So in today's lecture, we will talk about statistical inference of two model parameters, mean and variance of the normal distribution. In the last lecture, we talked about statistical Bayesian inference for the mean parameter of the normal distribution, assuming sigma square, the variance term is known. And this time we allow both of them to be unknown. So we want to make inference about both of them. Some concepts that are needed are nuisance parameter. So if you have multiple parameters, suppose theta is a vector containing several components, and suppose the first set of components, I call it theta I, and the second set of components theta n, and my main interest is in theta I, okay, theta I, and the second part I'm not interested, but they are still there in the model. I cannot get rid of them. But when I do Bayesian inference, I will obtain the posterior distribution of theta I given data. So how do I do that? First, I obtain the posterior distribution of all parameters theta I and theta n given data, and then I integrate out the parameter not of my interest theta n to get the marginal posterior of theta I. Now this integration, although it is defined in terms of this integration symbol, does not mean we will be able to do the integration. There are ways to handle this type of integration. We'll talk about it, and it depends on case by case, actually. It depends on the model, specific model. Another concept is conditional posterior. So let theta has two components, theta 1 and theta 2. Then the conditional posterior of theta 1 given theta 2. Conditional posterior means I'm interested in the distribution of theta 1 given theta 2 and data. And that will be the joint posterior of theta 1, theta 2 given data divided by the marginal posterior of theta 2 given data. And the denominator, the p theta 2 given data, is the marginal posterior of theta 2. Related concept, when we have nuisance parameter, suppose theta I is the parameter of interest, theta n is not of my interest. So what should we do when we specify the prior distribution? Should we just specify the prior for theta I and do not specify anything for theta n? No, that is not possible. We have to specify something strong or weak prior distribution for all the components of the model. And then if we are interested only in theta I, then we just look at the posterior distribution of theta I. And these concepts will be used in the following calculations. So normal model, suppose you have observations y1, y2, yn, and they are coming from this normal distribution with mean theta 1 and variance 1 over theta 2. Okay. And this theta 2 is called the precision parameter. It is the inverse of the variance. What is the parameter space? Theta 1 could be a real number between minus infinity to plus infinity, but theta 2 must be positive. A motivation for this parameterization in terms of the precision is that normal gamma family is then a conjugate family for the priors, conjugate family of priors for this model. And we'll see that a normal and gamma distribution prior gives you again a normal gamma posterior distribution. So what is the meaning of normal gamma prior? This is the prior. So suppose I assume theta 1 given theta 2 follows a normal distribution and theta 2 follows a gamma distribution. This is called normal gamma prior. Now, why do I take this form? This is very complex form, I believe. The advantage is, if I take this form, then my computation will be easy. Then I will obtain conjugacy. If I take something else, it will not give you conjugate prior or conjugacy. That is the reason we are taking this form. Question is, do we really have to take this form? Can we not work with some other prior distribution which is less complex? Obviously, we can do that. We can do that, but we'll come to that later. But first, I teach you what is the conjugate form, conjugate prior, and then we'll talk about the Jeffreys prior in this context. And then later on, we can talk about a very general prior for this model. And this distribution, normal distribution with unknown mean and variance, is one of the fundamental problems. And if we understand this one very nicely, we can generalize this concept to multivariate normal distribution also. So this prior distribution is called normal gamma prior, and the parameters are mu sub 0, kappa sub 0, a sub 0, b sub 0. So the last two parameters are for the gamma parameters, and the first two are for the conditional prior of theta 1 given theta 2. So what is the joint prior of theta 1, theta 2? Joint prior is the conditional prior theta 1 given theta 2 times the marginal prior of theta 2. And it is the density, normal density function times the density of theta 2. Density of theta 2. You see, when I write this prior distribution, I ignored the proportionality constant. Therefore, this symbol is used. I don't need to pay attention to the proportionality constant. It does not involve theta 1, theta 2. It only involves these hyperparameters. And these hyperparameters are known. Practitioners will specify the hyperparameters. Now, the question is, suppose I want to sample from this distribution, from this prior distribution, how will I do that? The marginal distribution of theta 2 is obviously gamma. However, the marginal distribution of theta 1 is not normal. Conditional distribution of theta 1 given theta 2 normal, but the marginal is a t distribution. And it is a non-standard t. This is called non-central t distribution. However, to enumerate the marginal distribution of theta 1, we can draw. So suppose you are interested in the marginal density of theta 1, and suppose you do not know the mathematical statistics. No worry, we can sample from the joint distributions, many observations, and simply take the theta 1 values, and based on those theta 1 values, if you draw a histogram, that is the marginal distribution. And this is the numerical technique. Now, how do you draw from this joint distribution? In order to draw from the joint distribution, first we sample an observation theta 2 from this gamma distribution. Given the theta 2, we sample theta 1 from this normal distribution. Okay, so this is step 1, sample theta 2 from this gamma, and step 2, sample theta 1 from this normal distribution. And we repeat this procedure maybe 10,000 times 20,000, 50,000 times, however you want. And in the end, you have bunch of theta 1, theta 2 values, maybe 50,000 theta 1 and theta 2 values, and you just consider theta 1 values. So this gives you an idea of knowing the marginal distribution of a random quantity when you know the joint distribution, and when obtaining the marginal distribution analytically is very difficult. So although here you can get the marginal distribution through mathematical statistics, but still it is very difficult because it's a non-central tree. Non-central tree has very complex density function form. Next is the posterior of theta. So here theta has two components, this theta 1 and theta 2. So the joint posterior is theta 1 comma theta 2 given data, and I can write it theta 1 given theta 2 and data, and probability of theta 2 given data. So the first term is the conditional posterior of theta 1 given theta 2 and data. How I get that? So that conditional posterior is obtained by writing the likelihood function times the conditional prior of theta 1 given theta 2. And the likelihood function has the following form, right? And the prior distribution has the following form, conditional prior. What I need the conditional distribution of theta 1, right? In the last lecture, we learned how to do the square completion. I can see clearly that the two terms in the exponents are quadratic terms in terms of theta 1. I just need to know how to combine these two quadratic terms. And that part we learned is called square completion. Square completion, if you apply this technique, eventually you will be able to write it in terms of this expression, theta 1 minus something square multiplied by some positive quantity with a negative sign. Now, what about the other terms? Yes, there were other terms, but they were free from theta 1. Therefore, I put the proportionality sign. Other terms that are not involving theta 1 and appeared as a multiplier is absorbed within the constant of proportionality. So clearly, you see that theta 1, the conditional distribution of theta 1 is a normal density function, right? Conditional distribution is a normal density with mean mu sub n, and variance is 1 over theta 2 times kn. How do you know that? Because I just identify it with the normal generic expression of the normal density. So if X follows a normal distribution with parameter m and tau square, then the density kernel looks like e to the power minus 1 over tau square and x minus m square over 2. So just looking at the density kernel, I can identify that theta 1, conditional distribution of theta 1 is again a normal density function with mean mu sub n and variance 1 over kappa n times theta 2. Now, what is mu sub n? So that mu sub n is the updated mean of this parameter theta 1 that absorbs information from the prior distribution as well as from the data. And it is n times y bar plus mu 0 kappa 0 over kappa n, and kappa n is equal to this kappa 0 plus n. Questions? Next, so the first task is done. Remember, we wanted to obtain the joint posterior of theta 1, theta 2 given data. The first part is done. Next, this task, obtaining the marginal posterior of theta 2 given data. Now, marginal posterior of theta 2 given data is the prior distribution of theta 2 times the likelihood of likelihood in terms of theta 2. So I have already integrated out theta 1. Okay. And how do you get it? So P theta 2 is fine, which is a gamma density. But to obtain the marginal likelihood only in terms of theta 2, you need to integrate theta 1 with respect to its prior distribution. So this is Py comma given theta 2 and theta 1 times P theta 1 given theta 2 times D theta 1. Now this part is the crux of the problem. For the normal distribution, this is the some of the integration are very important. And how do you do that integration? So we will calculate this quantity as follows. Note that given theta 1, we can write the observation yi as theta 1 plus epsilon I, where epsilon I follows a normal distribution with mean 0 and variance theta 2 inverse. Now mu, okay, so this is a type of mu. Instead of mu, it should be theta 1. Theta 1 given theta 2 follows this normal distribution. This is our prior distribution. So if I integrate out theta 1, then the distribution of yi follows the normal distribution with mean m0 and variance this plus this. We talked about this technique previously. That suppose you write y equal to theta 1 plus epsilon. This follows a normal distribution. This follows another normal distribution. Okay, and these two guys are independent. So if you have two independent normal random variables, if you add them, the total follows another normal distribution with the mean same as the total of the two means and the variance same as the total of the two variances. So y, after integrating out theta 1, that means you put the distribution of theta 1 there. Don't consider theta 1 given parameter. You put a distribution of theta 1. You put a distribution of epsilon. So then y follows a normal distribution with mean, which will be this plus this mean, and the variance this plus this variance. Now theta 1 theta 1 had a mean of mu sub 0. Okay, and let me write this part. Okay, so yi follows normal distribution with mean mu sub 0 plus 0. And the variance is theta 2 inverse 1 plus k0 inverse. So the density function, if you write the density of yi given theta 2, it is now yi minus its mean divided by its variance. So if you do the calculation, the variance turns out to be so this is the density, marginal density of yi given theta 2. Now, if you have n observations, then the likelihood function of theta 2 given the observed data will be the product of this density function. So it is the product over this guy, and it is k0 theta 2 over 1 plus k0 to the power n over 2 and e to the power this expression, and you sum this expression over I is equal to 1 to n. Now look at this expression. This expression only involves theta 2 as the parameter and the data. There is no theta 1. So the posterior distribution of theta 2 is this likelihood times the gamma prior distribution for theta 2. You clearly see that you can write theta 2, this is the theta 2 to the power a0 plus n over 2 minus 1, and over here it is e to the power minus theta 2 times this entire expression. And if you have the kernel, density kernel that any density kernel that looks like this, fx x to the power something minus 1 times e to the power minus something times x, where this dot 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 is positive and this dot 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 is also positive. This is the gamma density, right? So you clearly identify that this is a gamma density function. So the posterior distribution is again a gamma distribution with the shape parameter is the power that appears here, which is a0 plus n over 2. And the rate parameter that appears here in the exponent and as a multiplier of this theta 2. We call it Bn. So Bn equal to B0 plus this entire thing. So what you get is the posterior distribution of theta 1, theta 2 is the product of a normal distribution given the parameter given theta 2, and that theta 2 follows a gamma distribution. So it's the same structure as the prior distribution, normal gamma structure. Therefore, it is the conjugate prior for this normal family. Now, the question is, how do you, suppose your interest is in the joint posterior distribution. So I can write it nicely mathematically, but for the enumeration purpose, what should we do? We can sample joint from the joint distribution, many observations of theta 1, theta 2. So we first sample theta 2, and given theta 2 value, you sample theta 1, step 1 and step 2, and repeat this procedure many times. Then collect theta 1 values, calculate the average of those theta 1 values. That will be the posterior mean of theta 1. Likewise, you can collect theta 2 values and calculate the average. That is the posterior mean of theta 2. Similarly, once you collect theta 1 values, you can calculate standard deviation, which will be the posterior standard deviation. You can calculate credible intervals of the parameters. For theta 1, you just calculate 2.5 percentile and 97.5 percentile of the observed theta 1 values, and that is the credible interval for theta 1. Likewise, you do it for theta 2. Questions? If you are interested in calculating correlation, posterior correlation between theta 1, theta 2, you can calculate correlation of the pairs of observations. So here we denote theta 1, joint distribution of theta 1, theta 2, given data as normal gamma, and the first two parameters are mu sub n, kappa sub n, an and bn. An, bn are like this, an, bn, and mu sub n is right here, kappa sub n is right here. Okay, next we talk about objective prior distribution for this problem. Objective prior is the Jeffreys prior. So the log likelihood for a single observation y from the normal distribution, normal with parameter theta 1 and theta 2 inverse, is the following. Log likelihood is this. Now, why do we pay attention to a single observation while we have n observations in the data set? I told you, when you calculate the information, right? That information, if you have n observation, n independent and identically distributed observations, then your information for n observation is simply n times the information based on a single observation. And that n is just a constant of the proportionality. Therefore, it does not matter whether you calculate the information based on a single observation or n observations. So the log likelihood for a single observation looks like this. And Jeffrey's prior, the formula we know, it is the double derivative of the log likelihood function. And if you have multiple parameters, then you get information matrix. And that information matrix is negative expectation double derivative of the log likelihood parameter. And we take the determinant of that information matrix, take the square root. That is our Jeffrey's prior. So now coming back to the derivatives, this is the partial derivative with respect to theta 1 of the log likelihood. This is theta 2 y minus theta 1. Second derivative of the log likelihood with respect to theta 2 is this guy. And we need to take one more derivative, del 2 L theta over del theta 1 square, which is minus theta 2. And this derivative and the product derivative, where you take double derivative, one with respect to theta 1, the other with respect to theta 2. Then you take expectation of every term. Expectation of this term is simply minus theta 2. Expectation of this term is this guy. What about the expectation of the cross product term, of diagonal term? Expectation of y minus theta 1. Under the assumption y follows normal distribution, which means theta 1, that expectation is 0. That means your off diagonal term is 0. Therefore, the information matrix is negative of expectation of this double derivative of the log likelihood, which is theta 2, 0, 0, and 0.5 theta 2 to the power minus 2. Determinant is 0.5 over theta 2. Jeffrey's prior, remember, this is square root of the determinant. So this will be theta 2 to the power minus half. You see, I ignored this constant term. Constant has no value. Therefore, even if you calculate the information based on n observations, n will appear along with 0.5. That's it. And I will ignore it. No value. So with that, so now the prior distribution of theta 1 and theta 2 is theta 2 to the power minus 1/2. It does not depend on theta 1 explicitly. So the posterior of theta 1 and theta 2 is again conditional distribution of theta 1 given theta 2 comma data, and the posterior distribution of theta 2 given data. Now let us calculate the conditional posterior of theta 1 given theta 2. What is the conditional prior of theta 1 given theta 2? 1, right? Simply 1. Conditional prior. Because your joint prior distribution of theta 1, theta 2 is theta 2 to the power minus half. So the conditional prior of theta 1 given theta 2 is 1. So you just multiply here 1, and this is the data likelihood, observed data likelihood, which is 0.5 n theta 2 theta 1 minus y bar square. So this one, we need a little bit of practice. How I get from here to here, how I get it from here to here. Little bit of practice is needed. Our likelihood of data given theta 1 and theta 2 was e to the power minus theta 2 over 2 yi minus theta 1 square and theta 2 to the power n over 2, right? Theta 2 to the power n over 2. I ignored the constant of the proportionality, 1 over square root of 2 pi, no value. So from this expression, how I get from this expression to this one? So remember, I can always write this part as yi minus y bar plus y bar minus theta 1 square. And it is yi minus y bar square plus n y bar minus theta 1 square. In the last lecture or 2 lectures back, I showed you this type of breakup where the cross product term vanishes because yi minus y bar, sum of yi minus y bar equal to 0. So if I use this expression back here, theta 2 to the power n over 2, now keep in mind, what am I interested here? I'm interested in the posterior distribution of theta 1 given theta 2. Therefore, I will ignore this term. I will ignore this term, right? Because this does not involve theta 1. Likewise, this does not involve theta 1. So I'll just pay attention to this part. And that is what we have here. So now I can see clearly the conditional distribution and the prior distribution of theta 1 given theta 2 was 1. Therefore, the posterior distribution of theta 1 is a normal distribution with mean y bar and variance 1 over n theta 2. So finally, theta 1 given theta 2 and data follows normal distribution with mean y bar and variance 1 over n theta 2. And what about the posterior distribution of theta 2 given data? Let's look at that part. So the posterior distribution of theta 2 given data is the data only in terms of theta 2 and the prior distribution of theta 2. This you get it by integrating out theta 1 with respect to the conditional prior, which is 1 in this case, in the Jeffreys prior case. And the prior for theta 2 is theta 2 to the power minus half. And this one. So now we have to see if we integrate out theta 1, what happens. So let us look at the red color part. Integration of the data likelihood with respect to theta 1. So this is our likelihood of the data involving theta 1 and theta 2. And I want to integrate out theta 1. We apply the same calculation. Okay, so what happens? Yi minus theta 1 square written as yi minus y bar square plus y bar minus theta 1 square. I just did this calculation. This calculation is used many times. So it is better we get habituated with this calculation. This guy is n minus 1 sample variance S square. So when we talk about the sample variance of a set of observations, it is sum I is equal to 1 to n yi minus y bar square divided by n minus 1. So this is the sample variance. And the second part is n y bar minus theta 1 square. So I write it, this expression. Remember, we are integrating out theta 1. So this guy has nothing to do. So I just take it outside of the integration and keep this guy inside. When you do the integration of this guy, what happens? Okay, so keep in mind, these are the learning things we are doing. A lot of learning things happens here. Integration of this thing. Okay, so let's see. So suppose you have this integration minus infinity to plus infinity e to the power minus x minus mu. I'm just using notation, this type of notation, over 2 sigma square dx. Tell me, what is this integration? Exactly, very good. It is square root of 2 pi sigma. Now, how you know it? Exactly, because you know, if we put this down here, so divided by square root of 2 pi sigma, then right side is 1, right? Because this is the integration of the density function. So therefore, if you integrate out this, you get square root of 2 pi and sigma. Now, if we do, so suppose instead of sigma, you have a tau, okay? Tau is a positive number. Then what would happen? It would be square root of tau, right? In the denominator, square root of 2 pi and then square root of tau. So here, look at this integration. In this integration, theta 1 is what you are integrating minus y bar. So that square term, y bar has no impact. You see, in this integration, when you do the integration from minus infinity to plus infinity, this mu has no impact. Okay. So same thing, y bar has no impact, but the impact will be based on the scaling factor theta 2 times n. So this will appear in the denominator with the square root sign. Okay, with the square root sign. Where did I? Okay, so where did I adjust that? Okay, so I adjusted here, right here. I put the square root of n here and adjusted over here. So eventually it turned out it is theta 2 to the power n minus 1 over 2 times e to the power of this guy. For your better understanding, what I did, I multiplied this integration by this quantity and divided by the same quantity, so that this integration now becomes 1. This is the normal density integration. So wonderful. So you get the data in terms of theta 2 after integrating out theta 1. Now the posterior distribution of theta 2 given data is this guy times the prior distribution theta 2 to the power minus half. This is the Jeffreys prior, which is theta 2 to the power n over 2 minus 1 and this guy. So theta 2 given data follows gamma distribution with shape n over 2 and the rate parameter n minus 1 s square over 2. N minus 1 s square over 2. There are a lot of typos. I will correct them today. So what happened here again with the Jeffreys prior, your posterior distribution is a normal gamma distribution, normal dash gamma distribution. What does it mean? It means given theta 2, the conditional posterior of theta 1 follows a normal distribution and a theta 2 follows this gamma distribution. Questions? In the next class, I will do one example, real data example, show you the code and show you how to generate data, very simple, from this joint posterior distribution. Step 1, sampling theta 2, then sample theta 1. Okay, why I'm sampling theta 2? Because in the joint distribution, it is written theta 1 given theta 2 times theta 2. Theta 2 I can sample marginally, but theta 1 depends on theta 2. Therefore, first theta 2, then theta 1.